So some of you asked about this question here and the relationship between the two molecules. So I've built out these molecules for you. I have a carbon, oxygen, oxygen going back, bromine coming forward, chlorine coming forward, fluorine coming back, CH2, CH3. This is the molecule on the left. I then have OH, OH, Br coming forward, just like before. And then fluorine coming forward, chlorine coming back, so that's switched. That's the opposite of how it was in the other molecule. CH2, CH3. All right, so the first question I'm asking myself are there any chiral carbons? Well, I see this carbon in both molecules, not chiral because I have two of the same groups. This carbon, I have 4 different things, so it is chiral. I'm also recognizing that these two molecules have exactly the same atoms attached to exactly the same carbons, so they are isomers or potentially the same molecule. So I know I don't have diastereomers because I only have one chiral carbon. Diastereomers can only happen with 2 or more chiral carbons. 2 or more chiral. Conformational isomers, well, the way that I have these drawn, there's exactly the same bond angles. I haven't indicated anything about the CH2, CH3. Could you form a conformational isomer here? Yes, absolutely, but that's not what's being shown. So I'm gonna cross that off. So I have enantiomers are same molecule. So let's figure out if we have the same molecule. Let's figure out if these are superimposable. A little tricky, but we can do it. So this carbon I don't really care about because it's not chiral. This is a carbon that is chiral. And let's line it up as best as I can. Well, if I line up my ethyl groups here, I see that my molecules actually did not line up. So not the same molecule, not superimposable. Kind of by process of elimination, that leaves enantiomers. Do we have a mirror image? In fact, we do. You can see that the fluorines and the chlorines line up with each other. We can just rotate around a single bond to make those ethyl groups look exactly the same. So it is indeed a mirror image. Okay. The other question I got was this giant molecule that we have here. So I've built it out for you. I have my benzene ring. I have this cyclical molecule with 2 oxygens, which you see here and here. Nitrogen is coming out towards me based on this carbon that I'm highlighting. So based on this carbon here, the nitrogen is coming out. Of course, it brings the rest of these molecules out towards the viewer as well, but we just indicate that with this single dark line, the single wedge-shaped line. You can see the hydrogen is headed back. I have my carbon with a double bond oxygen. I have my nitrogen and hydrogen. I have my, notice nitrogen is making 1, 2, 3 bonds. This empty bond is just a product of how the pieces were built, so that doesn't have any chemistry significance. I have my carbon with my double bond oxygen right here, and then a CH2, a CH3. All right, so I need to figure out what's going on between this molecule and this molecule. And I'm thinking that I see between these two molecules, they have exactly the same atoms and exactly the same carbons. So my guess is that they're either isomers or the exact same molecule, just a repeat of the same molecule. So my job is to figure out which one. I suspect they're stereoisomers, so I'm gonna check if there's any chiral carbons. I see there's actually only one, this carbon right here. All of these carbons are forming only 3 bonds because of double bonds, so those cannot be chiral. I then have this carbon forming double bonds. I have carbons with two hydrogens, which are of course not shown in skeletal formulas, but they're still there. So not chiral, double bonds. So not chiral. So this is the only chiral carbon that we have. All right, so we really only need to consider the chiral carbon. The rest of this molecule is sort of getting in our way. So I actually did not have all the pieces to build out the other molecule, but let's actually just get rid of these because they're just kind of extra space. We're not going to consider these. We're really just worried about the chiral carbon. Is the chiral carbon superimposable, meaning same molecule, or does the chiral carbon make a mirror image, meaning enantiomer? So I'm going to get rid of some of these just to kind of save space so we can really focus on the chiral carbon. So here I have this carbon, I have my nitrogen pointing out, my hydrogen going back, and then some alkyl groups up at the top, and the carbon-oxygen group at the bottom. All right, let's take a look at the chiral molecule from the other side. So I have here, so this one I'll put aside for a moment. So let's take a look at this chiral carbon. I have my carbon with hydrogen coming forward. It's coming forward and up in the picture, which I can show you like this. Nitrogen going back. Of course, the nitrogen would have that big benzene ring. This whole benzene mess would be attached here, but we don't consider that for chirality. So I'm just not going to show you that. So we can focus on just the chiral carbon. We have our carbon with our oxygen, and of course there's other things attached here, but we're really just figuring out this chiral carbon superimposable or mirror image. So let's try to superimpose. I'm matching up my oxygens, I'm matching up my alkyl groups. Oof, looks like my hydrogens and nitrogens don't match up. So let me switch things around, and I do indeed get a mirror. I get the hydrogens lining up, the nitrogens lining up, the alkyl groups coming straight up, and the carbons with the double bond oxygen going back. All right, hope that helps. All right, so after seeing those two examples and recognizing that you don't have a model kit when you take the IB test, you're probably asking yourself, how do I decide if two molecules with chiral carbons, another way to say that is just two chiral molecules, how do I decide if two molecules with chiral carbons are the same molecule, just two of the same molecule, enantiomers, or diastereomers? This word is hard to spell. Hopefully I got it right. All right, so there's a couple things that you need to keep in mind. The first question you ask yourself is there one chiral carbon? Or is there two? Or are there two or more chiral carbons? If there are two chiral carbons, you have two options. If there's one chiral carbon, you have two options. Same molecule or enantiomers. Well, we know it's the same molecule if it's superimposable. So if it's not superimposable, it must be an enantiomer. Enantiomers make mirror images. Sometimes that's really, really hard to see. It's hard to hold these molecules in your mind in 3D and flip them around to exactly see what the mirror would look like. If the IB asks you why are they enantiomers, it is indeed because they form a mirror image. But if you're sitting there trying to decide, this is a good process of elimination. If you have one chiral carbon, you only have two options, same molecule and enantiomers. Even if you're not seeing the mirror immediately in your head, if you can see that the two molecules are not superimposable, then your only option is enantiomer. If you have 2 or more chiral carbons, you have, of course, the same molecule. And then you would need to check each chiral carbon. If all of them are superimposable, then you'd have the same molecule. You have enantiomers. In this case, again, you would need to check each chiral carbon to see if they make a mirror. Or diastereomers, where they're not the same, but they're also not enantiomers. So maybe, for example, 1 chiral carbon is superimposable and 1 forms a mirror, for example. I hope that helps. Good luck. Bye.